Good morning. Last week of classes, can you believe it? Ah, It's crazy. With a little bit of well, I guess not luck on my part. With a little bit of work, we'll be able to finish the material today, but also just talk about the final exam outline, which is all I really do in terms of review. Which leaves Thursday, just I'll be here if you want to work through questions together. But I know that it's a busy time of the year. And so I know you have other things going on. And so, what I want to say in my notes here is that we will finish material today. So, we'll finish uh, all the material today. It's crazy. And sad. Mm, So sad. I know. I'm not even sad. It's exciting. And review topics covered on the final exam. Thursday will just be kind of a drop-in session. So Thursday, uh, I will be here. I will be in the Zoom room to answer questions, but no class. Well, I'll be there to answer questions. So if you want to sit in on that, and if you have any questions, right, that you want to go through, then that's what I'm thinking that that's going to be reserved for. Okay, so I want to finish all the material first, and then yeah, kind of a cliffhanger, I guess, and then go through the topics of the final exam. It's not a cliffhanger because uh, it's already posted on Moodle. Let me see if I can get there. Um, it's not our course. Here's our course. Um, and I'll switch my role to student. Down here at the bottom, you have your final exam. So I just want to talk about what each of those parts mean, kind of lumped into 10 different things. And so that's what to expect. And then I've also posted the practice for the final. Um, that's in addition to the practice that I posted for test 1 and test 2. Those might be worth reviewing. And so this is just additional practice with regression included for question 10 and 11. Right, those are the new topics that we haven't been tested on yet, as well as two independent sample means. So you'll see some of that on here as well. And the solutions are posted, and they use the t-table just like we've been doing in class. I can post the z-table version as well, but I don't want to overwhelm people with the two different versions. So if you want them, I can post them, but I won't unless I hear otherwise, because I've been using the t-table in class. So that's what we have to look forward to. And now what? Section 8.3 is we're just going to briefly talk about outliers. Outliers is a term that we use, in regular speech. And if we sit down and think about what does it mean, well, it means something that's outside of the norm, right? So something outside of where we would expect it to be, right? And that's exactly what we have in outliers in regression as well. And so There are a couple of different types of outliers. I just want to mention them. They're not important. I'm not going to test you on them. Just being aware of outliers and what we do with outliers is the more important part. But to kind of get us there, and I'm finding I need to, because you guys can see my pen there. Oh, that's weird. See how I do. Okay. So how do outliers influence this least squares regression plot? Oh boy, now I've done it, haven't I? Come on. Down there. We'll see. So if we look at this, oh my gosh. Good thing I'm calling it quits after today's class. Can you imagine? This is nuts. How do I delete this? Show keyboard. Delete it. I don't know. It's like I've never done this before. Back on track. Okay. So, if even if we didn't have this line here, we've got this cluster of outliers, right? And so one of the main concerns would be it looks like this line is being pulled towards these outliers, right? Remember, the least squares regression line is just trying to minimize the distance between the line and all these points, right? And so it's going to be pulled towards outliers. And so that's going to be a problem when we include these outliers in our analysis, right? Because if we removed the outliers, I suspect that our line would look something more like this, right? Doing a better job, maybe, yeah, I'm just freehanding here. So, but it would do a better job of predicting the main event. So those main points on our scatter plot. Whereas as it stands, these outliers are pulling the regression line towards themselves. Okay. And so without the outliers, the regression line would be steeper, right? That's what we kind of established here. And it would just be closer to this group of observations, the main event, as I think of them as. Um, and so one of the things that we are faced with when we have outliers is what do we do with them, right? And so one of the things that is kind of annoying, I guess, is that's your call. And so you can argue it either way. And so how are we going to argue whether I should keep these outliers or remove them? So one of the options is we just remove these data points, right? We can analyze them separately if there's enough of them, right? You have to make a note in your report saying, hey, I removed these outliers because, why? Because they were pulling the line towards them, right? And so what you would do is you would fit the line. So here you would fit this line with all the outliers included. And then ideally, what you would do is you would pick away at the most extreme outlier, right? One at a time, refit the line, see if there was a change in the slope, right? Because the slope, right, changes here. We can see that the slope would change. And so if there's no change in the slope, right, when we remove these, then what's the point in removing them? But if the slope changes, which in this case we suspect that it would, right, then we would say, okay, because I prioritize being able to predict these values, right? Instead of just these values and not these ones very well, then I remove these outliers in favor of being able to predict these values better. Okay? Stronger predictions. We can also have a scenario like this, right? Where we have this one outlier over here, but if we just zoom in on this cluster here, there's no reason for this line to move like this, right? If we're just here, this line, we could have a slope like this, we could have a slope like this, but really what is more likely is that the slope would be 0, right? Because if it can move around like this, then where it lands is just a horizontal line, which is a slope of 0. So what I'm going to do here is I'm going to remove those just in case they're um, confusing anyone. This 0 has nothing to do with the slope. That is just coincidental. Okay, so here, rise over run, well, there's no rise, so the rise is 0. Over run, well, the run can be infinite, and it would still be 0. 0 divided by anything is 0, right? And so here you'd have a slope of 0. Okay? If you didn't have this point out here, this kind of uh, extreme outlier that's anchoring the point, and that's the only reason that we have this very strong slope going on. Okay, and so, right, if we didn't have this outlier, then the slope of this relationship would be 0, and we wouldn't be interested in that, because what does a slope of 0 mean? A slope of 0 means that there's no no relationship between x and y. Uh, In terms of the terminology, we'll just run through it, but it's not something that I'm expecting of you. It's just to be aware that there are different types of outliers, but just calling them outliers is enough. Okay, and so outliers are, of course, points that lie away from a cloud of points, whether they're showing a relationship or not. If they're far away, then they are outliers. And so outliers that lie horizontally away from the center of the cloud are called high leverage points, right? If you think back um, to physics, right? Leverage, if you're out here, right, and you've got an outlier up here, then you've got this leverage, right? And so high leverage points that actually influence the slope of the regression line, those are called influential points, right? And so, right, if we had a relationship here, if this was a strong relationship, right, we can have a strong relationship and then we can have a point. And I know there's an example maybe a little bit later, so I'm not going to draw it on here. But if we had a strong relationship that followed this line, right, then this point wouldn't influence the slope, right? So it is high leverage, but it's not influential. Okay, and so that's the difference. And so what you're going to do is to determine if the point is influential. And if it's influential, then you're going to want to remove it from your analyses. Okay. You can visualize or actually fit the model or fit the model. Fitting the model, when I say fitting the model, might be getting ahead of myself, but what I mean by fitting the model is find the slope and find the intercept of the line of best fit, right? And so you would use Excel or some other software to do that, which you have or will see in Lab 10 once you do it. But I saw a lot of you have already done it, so that's great. Um, and so it's very easy to fit the line and fit the model in Excel. Yeah. And so it's easy enough to remove some points and then fit the model, see how the slope changes. So does the slope of the line change considerably? Okay. And so that's what you need to ask yourself. So if so, then the point is influential. If not, then it's not an influential point. And so here, if if the slope of the line changes, then you could argue removing the point. So then you would argue um, it would be better to remove the outliers, potentially more than one, from the analysis. Right? If it's not an influential point, right, then we can keep the points in the analysis and it's not going to make a difference, right? Then we could argue it would be better to keep the points or keep the outliers. Again, potentially more than one. So an example, right, of some influential points that we could have. So here we have these points, and so this is the log of the surface temperature and the log of the light intensity of 47 stars on some cluster. Now, I don't know what that means, but I know what a scatter plot looks like, and so that's the only thing that we really care about. And so here I've got these outliers, right, clearly very different from this general relationship out here. And so when we fit the model without the outliers, then of course this line of best fit does a decent job of predicting values for values of x between 3.8 and 4.6. Right? We talked about extrapolation last week. And so we don't want to extrapolate because here it looks like we have a different relationship. Okay. And so with the outliers, the line would look like this, and it would do a terrible job of predicting anything really besides these values here maybe, right? But this red line would do a way better job. Okay. Okay. I don't need you to remember the difference between leverage and influential, or high leverage and influential. And so here, this one is high leverage. Because it is far from the cloud of data, right? But it's not influential because it's not affecting the line. So this is the example that I was thinking of, right? So not influential because it's in the line of fire, so to speak, right? And so here, this outlier, right? It doesn't really influence the line very much. Okay, and so we can have these outliers, and they're not really pulling the line towards themselves, right? They just happen to have a high residual, the residual being the distance between the line and the observed point, right? And so, um, okay, I don't like this one because it's none of the above. Which of the following is true? None of those are true, and I don't like that approach. But what we can talk about is the difference between the R squareds. So remember, the R squareds is the percentage of variability explained in Y, explained by the least squares regression line on X. We talked about that last day. And so that's a common goodness of fit measure, in the sense that if you have a higher R squared, the better our line fits our data, right? And the better our model is, right? And so if you have a correlation of 0.08, that's a very weak relationship, right? And so if you have this cloud here, right, there's no relationship here, and that's reflected in the R squared, right? This line it doesn't do a very good job of predicting anything because there's no relationship, right? Whereas if we have a high R squared, or high correlation, thus R squared, right? Correlation squared is R squared. Right? And so, but that's only courtesy of that line. This cluster looks very similar to this cluster. And so now with this outlier, we have this kind of inflated R squared, making us think that, oh, this line does an awesome job at predicting data, but it doesn't. So that's all I want to say about outliers. Okay. And so ultimately, it's your choice. What do you want to do? If you're faced with an outlier, you should remove it, see what happens, and then make a decision from there. If it doesn't change your regression line, then I would argue just keep it. Right? You always want to keep as much data as possible. Oh, that doesn't look very nice, does it? section 8.4, and the reason I want to bring this up is because you've seen it in lab 10, and so it might be nice to talk about it a little bit. I also posted a bonus lab. I can't remember if I mentioned it. I posted a bonus lab on multiple linear regression. And so that is section 9.1 in your textbook. We're not going to cover it, so that's why it's a bonus. But it's just adding more values of x than just one. So simple linear regression refers to just one value of x, and then multiple linear regression has more than one value of x. Okay. Okay. Just want to talk a little bit about the background here. Okay. And so we saw, or we have seen, that if there is no relationship between x and y, right? So something that looks like this, right? No relationship here, right? I don't see a pattern, I just see a cloud of dots, right? And so what we would say is then that the line of best fit, then the line of best fit would have a slope of 0. Oh, what the? Okay, I'm going to move this back up here where I'm used to it. A slope of 0, right? We would have this slope, so b1 equals 0. Okay. So what do I want to do, or what could I do? Thinking about inference and thinking about hypothesis testing, right? If I want to know if there's a significant relationship here, what would I want to test? I don't want to test about the sample information. I want to test about the population, right? So I want to test whether the population slope, beta 1, is it equal to 0, right? Meaning no relationship between x and y. Or alternatively, is it significantly different from 0, meaning that there is some relationship, right? And so here, this means no relationship, no significant relationship between x and y. And here, there is a significant relationship. In fact, we're going to frame it in the sense that x is a significant predictor of y. X is a significant predictor of y, right? And so that's technically what the output is going to tell us. We're not going to do any calculations here, but I just want you to have seen output because that's what you're going to use for regression in real life. Okay. And so here's some kind of weird data that I don't know. In 1966, Cyril Burt published a paper called The Genetic Determination of Differences in Intelligence, a study of monozygotic twins reared apart. I don't know why there's a question mark here. But that's okay. The data consists of IQ scores and we're going to have to assume that it's a random sample of 27 identical twins. Unlikely, right? Because one was raised by foster parents and the other was raised by biological parents, which is just a very strange situation to me. But anyways, it was 1966 and I guess anything went still. It's weird. Uh, who knows? So we have this sample of 27 identical twins. They're raised by different parents. And then they've measured the IQ of those raised by biological parents and those raised by foster parents. And they find that there's a strong positive linear relationship, right? In fact, the correlation is 0.882, which is quite strong, right? And it's positive. And here we see that there's a linear relationship. So I want to make a note here. This is a strong, positive, linear relationship. Whenever you see a scatter plot, oops, you should describe the relationship, right? Strength, direction, and whether it's linear or nonlinear. Okay. So what we can do is we can use software to generate the equation of this line. Okay. And so what that would look like is something like this. Now, this is R output. R is a statistical programming language that we're not using, but the Excel output looks the same. Okay. And so here, I just want to make a note that, and I'll do it in green. This is R output, but Excel output looks very similar. Okay. So we have these coefficients, which they call the estimates, but I'm pretty sure, I can't remember what the Excel output, I might call it the estimate. This is the estimate of the intercept. Okay. And so this means that this is B0. Okay. The estimate of the intercept. The estimate of the coefficient of the biological IQ is 0.90144. So the slope for this line is 0.90144. We have biological IQ because that's our X value, right? And so here, X and X is the biological IQ, and we're trying to use, what are we trying to use this for? We're trying to use the biological IQ to predict the foster IQ, right? We're always trying to predict the Y, right? Regardless of what makes sense, right? Whatever's on the y-axis is what we're predicting. And so we want to predict um the foster IQ using the biological IQ. Okay. So from here, what we have is the foster IQ, the predicted foster IQ is going to be the intercept 9.2076 plus 0.90144 times the biological IQ. And so we have 9.20760 plus 0.90144. And I'll just bump this over a little bit. Times the bio IQ. And I just want to highlight where these things came from, right? So here and here. Yeah. Because in general, you have y hat is b0 plus b1x, right? And we've seen the work that you would need to do, and it's not hard, right? You need the means and the standard deviations, which you can easily calculate. You need the correlation, right? And then you would find the slope and then the intercept. But this is a lot easier. You can just grab it from the output. Now, we've ignored this part until now. There's a standard error for each of these estimates. Uh-oh, you're having flashbacks, I can tell. I know. Right, flashbacks, why? Because this brings us back to hypothesis testing, confidence intervals, right? In fact, we're going to calculate a t, or they've calculated the t for us. Okay. And then we've got the probability that it's greater than or equal to the absolute, or greater than the absolute value of t, which is just the p-value. Okay. And so these are p-values. Okay. In fact, it's the probability, and we only really focus on the p-value for the slope, right? And so the p-value for the slope is very, very, very small, 1.2 times 10 to the negative 9. So that means you move your decimal 9 spaces, right? So there's 8 zeros there, I think, uh, until you reach 1, 2. So it's very, very small, which means what? It means that the slope, what's the null value that we were testing against? Well, it's what we discussed up here, right? Is the slope significantly different from 0? Sorry, I should have been on H naught, right? Is the slope significantly different from 0? That's what we're interested in. Well, if we find a p-value of 0.000000012, I don't know how many zeros I said, hopefully 8, then we have enough evidence to reject H naught and conclude that this slope is significantly different from 0. Okay. And so that's how we determine if a predictor, an X, is doing a good job of helping us predict the Y. Okay, we can use that p-value. Okay. Which of the following is false? Okay. I don't like these. Wanted to talk about, no, because it looks different. Don't worry about that. Don't worry about that one. Stupid. Stupid. This is just highlighting. So the multiple r squared is the r squared, so 78%. Okay, fine, I'll talk about it. The r squared, right, remember, is the proportion or the percentage of variability in y explained by the least squares regression line on x, but it does not mean that 78% of the Foster twins' IQs can be accurately predicted by the model. That's not what it means, and that's what it's highlighting. And so here, this multiple r squared, it's just highlighting that the r squared has a specific, so instead I'll say what it is. R squared is the percentage of variability in y explained by the least squares regression line on x. So it doesn't mean that 78% of the Foster twins' IQs can be accurately predicted by the model. That's not what it means. It means r squared. It's the percentage of variability, so the percentage of activity explained by the least squares regression line on x. Right? And so that's the difference. I do need you to know what r squared is, right? And I could give you the r squared to calculate the correlation, right? By taking the square root, checking the scatter plot to see if you have a positive or a negative relationship. If you have a negative relationship, then you add on that negative onto your correlation that you found, right? But besides that, I don't expect you to go that deep into r squared. Okay, so what we were saying is that assuming that these 27 twins comprise a representative sample of all twins separated at birth, Okay, fair enough. We would like to test if these data provide convincing evidence that the IQ of the biological twin is a significant predictor of IQ of the foster twin. What are the appropriate hypotheses? Okay. And I'm going to use this kind of as a review for general hypothesis testing, right? What are some general facts that we know? Well, hypotheses have to be about the population, right? So in this case, it has to be about a beta. Beta represents the population. So beta naught is the population intercept, and beta 1 is the population slope. So right away, we can eliminate A and C, right? Because uh, hypotheses must be about the population. Yeah? So, if we want to test if something is a significant predictor, right, then we're talking about the slope. And so that means that we're not talking about beta 0, that's the intercept, right? And so here, this one is no. This is testing the intercept. Specifically, if it's significantly different from 0, and that's not something that we're interested in. And so, there are rare instances where that might be something that we wanna know, but in general, we wanna test if the slope is significantly different from 0. Okay, and so that's why we wanna pick D. Okay. So here, this is our p-value. If we wrote it out, whoops. If we wrote it out, right? So here, the intercept is not significantly different from 0, right? That's not of interest. Here, the slope is significantly different from 0. Okay, meaning that you have a significant predictor. Since the p-value is approximately 0, the bio IQ is a significant predictor of foster IQ. Uh, it's based on the test statistic, the t-test, but at this point, we're not going to be calculating the t, right? But it is taking the estimate, how far is the point estimate from the null value, which is 0, taking into account the standard error for each estimate, and then using t and some degrees of freedom. We're not going to talk about that while it's here, but the degrees of freedom for the slope is n minus 2, where n is the sample size, but that's built into this p-value here, so you don't need to worry about that. Okay? All you need is this p-value and the estimate to build your model. Okay? So here, this slide does go through it, but I don't want to do that. Oh, I don't remember this example at all. And I think, what time is it? I think what I want to do, so you've got this other example with more regression output if you're interested, but I think what I want to do is um call it on the new material. So no new material. Let me just scroll through here, blah blah blah. We can make a confidence interval for the slope if you wanted to. We saw that sort of in the example of extrapolation. Right? But for us, The end. Good. That's the end of new material. Now let's talk about the final exam. And so let's see here. Oh, look, just switched to paper. Nice. And so um you did it. Good job. Or maybe how can I generate some balloons here? Yee! You did it. Congratulations. That's the end of uh uh oh, you can't find it on Moodle, huh? Well, I'm gonna go there. It's at the very end.
So when I've got, if I go to final exam on the Moodle, you just get the practice of final, and then it's got the solutions. Those are the only two that I can see under final exam tab.
And it doesn't have this breakdown?
Oh, sorry. I found it. Sorry about that.
Good. No worries. Glad you found it. Um, let me take a screenshot of this because I want to talk about, I guess, confess. Insert. Not really a confession. Don't worry. I'll do this first. So today, we talked about the types of outliers. We talked about inference for linear regression, right? That's what we just talked about. And I did it very briefly, just because it's not on the final exam. And so I'm not expecting that of you. And here's my confession. We could have multiple regression, right? Multiple values of X, which I'm not covering, but you can see the bonus lab. Right. And then what I'm doing is I'm sneaking this final exam review into today. Okay? And this is lab 10, the linear regression lab, and potentially the bonus lab if you want to boost your lab grade. Otherwise, it's set to drop your lowest one. So if you don't do it, then it's fine. Okay. Now let me crop this up here. Hate it when it does that. So of course, you guys have an online final exam, but I'm gonna try to mirror the in-person final exam as much as I can in terms of the layout. And so this is a typical layout of the final exam. It's a little bit mysterious, right? Which we'll see when we hit kind of points 5 through 9, right? Anything goes. And so what I want to do is just talk about these are approximate marks. I do want to highlight that because I reserve the right to make tweaks. I have not finalized the final exam for you guys yet, and so I'm reserving the right to change it if I want to. But roughly, okay, so just a rough idea of where these marks are going to come from. Okay. We'll start off with some multiple choice questions. Relatively straightforward, right? Chapter 1, chapter 2. Let me see here. So here, paste image. Right, this is from test 1. And it'll be on chapters 1 and 2. And multiple choice, 10 marks. Easy enough. Okay. Second chunk, because they're not necessarily just one question for you guys, but kind of the second category of questions. Whoops. Uh-oh. How do I? There we go. There's an or here. Okay. So either it's a contingency table with the associated probability calculations, right? And so we saw that on test 1, and it's in chapter 3, or a tree diagram. So I'm not going to make you do both like we did on test 1, but it's going to be one or the other, and you need to be prepared for either. Okay? And so it could be a tree diagram where you draw the tree and you figure out your probabilities from the tree diagram. Third one, third chunk of questions is the normal distribution to find probabilities and cutoffs, right? And so this is Z-scores. Z-scores. It was on test 1. And it's chapter 4. Okay. Yep. Chapter 4, 4.1 in fact. Let's do that. Section 4.1. Okay. Try to be as specific as I can. Okay. Also, you've seen it on test 1, right? If something follows a normal distribution, and you find that a score of 30, what's the probability of someone less than 30, someone more than 30, that kind of thing. And so be prepared to do that, but also working backwards, right? Where we have some probability and you're going to find the cutoff. Here's another or, keep you on your toes. The fourth chunk is binomial probabilities with the normal approximation. So we did have this on test 1, or the Poisson distribution, which you had as a bonus assignment. Good. I didn't say anything. Okay, and so here, this you saw on test number 1. And I think the normal approximation was the bonus in that case, but that was to prepare you because we did talk about it, but we just hadn't covered it recently or kind of far enough in advance for the test. So that's why I made it a bonus, but it's fair game for the final exam. And this is section, I want to say 4.3. And then the Poisson, I think, is 4.5. I could be wrong. Well, okay, fine. I'll check. Where's that table of contents? At the beginning, probably. Uh, feels good. I was right. Okay. So you haven't been tested on the Poisson. It was that bonus assignment. But you have been tested on the binomial and the normal approximation to the binomial. Here's where it gets a little kind of lofty. Oops. So I'm going to keep these together. confidence interval, goodness of fit test, that's for sure, right? So this is 6.3. The chi-squared goodness of fit test. You saw that on test 1. No, test 2. Oops. Oops. A confidence interval, a goodness of fit test, another confidence interval, a hypothesis test, right? And so just be prepared for all these different questions that we could have. Okay? This might be a good time to refer to that document that I posted, right? And so these were all on test, wait, whoa. Nope. These were all on test number 2, or 2 independent sample means. Which we did not have on test 2 because we had just covered it the day before the test and it just didn't feel fair to include it. But now it's fair game. In fact, I would bet money, if I was studying, I would bet money on that you're going to have to do a 2 independent sample means question fully because it has not been tested yet, right? Will it be a hypothesis test? Will it be a confidence interval? Well, I don't know. So you can practice those. Okay, couple of notes here. On your Moodle page, I posted, so in the test 2 week, I posted this decision tree with formulas. Okay, and so all of these are fair game. Of course, we didn't do 2 independent, or the chi-squared test of independence. Oh, I don't have a pointer on here, so that's kind of annoying. But we didn't do the last of the proportion ones, and then we didn't do ANOVA. I posted a bonus assignment on ANOVA, but that's not on the final exam. But here it goes through all the different things that you could be tested on in terms of confidence intervals and hypothesis testing. And these formulas are from your formula sheet, right? And so then you can use it as a guide, especially because you're working open book, right? It might be nice to be very familiar with this table. Let's see here. If you haven't already, I made the adjustments to test 2. Good work. But feels like forever ago, but I can't remember when I finished. Last week sometime. And so you should be able to go in and see it, and you should see feedback that I left you. So if I make adjustments to your grades, or if there's little pointers that I want to make, so you don't make the same mistakes, then I've left those in the feedback. Okay. But there's something else. Oh, and I also gave you that inference decision tree as a Word document so that you can add things if you want to. Maybe remove things, I don't know. Okay. See decision tree posted on Moodle. Oops. Say that. Okay. Good chunk of marks here coming from inference, right? And so that's going to be the meat and potatoes of what we're doing here. And then finally, oops, the least squares regression analysis is the thing that another thing that we haven't been tested on yet, right? But this is chapter 8. Chapter 8, which we just finished. Okay. And what are some of the questions that you'll need to answer? Right. A. What's the response and the explanatory variable? Response and explanatory variables. What's another thing I could ask you? All right, I could ask you to describe the relationship. So given a scatter plot, describe the relationship. You have to talk about all three things, right? The strength, the direction, and whether it's linear or nonlinear. Of course, it's going to be linear, otherwise we can't fit a line to it, right? So that one's gimme, but you have to say it. And then this is where things can kind of branch off, right? Either you're given the correlation, right? And so kind of the two scenarios. Scenario one is you're given X bar, SX, Y bar, SY, and the correlation. Okay. Or in scenario two, and the practice for the final exam document that I posted gives you practice for both. Okay. Then you're given X bar, SX, Y bar, SY. And then in a question, given R squared and asked to find R, the correlation. Okay. So those are the two scenarios that you're up against, right? So one way or another, you're going to have the correlation, right? I just give it to you and then you use it to calculate the slope and the intercept, right? And so you knew that was coming. Or I give you the R squared, which means you have to know what it is, right? When I tell you the definition, right? And then I ask you to find the correlation. So from there, right, regardless, you can find the slope. That's from your formula sheet, right? On your formula sheet, where is it? Wait, don't want to delete it. Oops. Okay, so if you find the slope, then the slope is this little guy, right? The correlation, that's why you need it. So one way or another, you're going to have it times the standard deviation of the y's divided by the standard deviation of the x's. So of course you need all that information. Then what do I get you to do? Well, you have to interpret the slope. You have to interpret it in terms of the question, right? Interpret the slope. Yeah. Then you're going to find the intercept. Which is also on your formula sheet. Copy. Then interpret the intercept. Huh? What was our overall goal? Well, it was to build the line to make predictions. So then use y hat equals b0 plus b1x to predict y for a given value of x. you're going to beware of extrapolation, right? And so here, HI, so many parts, right? Beware of extrapolation. What's extrapolation? Extrapolation is when you use this line, which is your best guess, right? But you use it to predict for values of x outside the range of your data, right? Outside the values of x in your data, right? That's extrapolation. Okay. And then this isn't really a part, but maybe I'll do it as a subset. Beware of extrapolation, right? Usually I'll say, do you trust this prediction? Right? And then you would say no, because it's an extrapolation. Okay? And I might get you to do two predictions, right? One that's not an extrapolation, one that is, and then ask you if you trust the predictions. Okay? And then of course, if I didn't give you the R squared, right? If I didn't use the R squared up here, so if it's scenario 1, then usually what I do is I get you to find R squared, right? Calculate the percentage of variability explained in Y explained by the least squares regression line on X. And then that's it. Easy. Not easy, but that's all there is to it. Okay? And so, and I can't believe we did that. Oh, just like that. Congratulations. We're done the course. And so, like I said, I'll be here on Thursday if you have any questions or if you want to work through any problems. Then you can bring those, but I'm not going to be bringing my own problems. I'll be here if you need me. Otherwise, good luck with the rest of your courses. I know it's a busy time. Just hang in there. Got it. For the final exam, I guess I should say I will be. Oops, I will be in our Zoom room for the final exam. I'm also doing an in-person final at the same time, and so I'm definitely not expecting you to be in the Zoom room, but I'll be there if you have a question, in case you have a question. But besides that, just like the tests, I don't expect you to be in the Zoom room unless you want to be. Okay? But you do not need to be in the room, be in the Zoom room, unless you want to. Okay? So like I said, congratulations, that's it. Now you have a clear overview of everything you need to know, hopefully. Good luck, have fun, and maybe I'll see you on Thursday. Thanks, guys. I'll stop this recording.